Thank you for coming to my talk. I'm Younjin Kim. I'm from KAIST. Today, I'm going to talk about the extremal combinatorial problem of Noga Alon. This work made over the past 2 years while I am KAIST. So, who is Noga Alon? Yeah, he's one of the famous mathematicians in the combinatorics area. And he has published more than 400 papers in the extremal combinatorics. And he also has received a lot of prize, from Edwards Prize to Emil Prize. What is extremal combinatorics? It determines the estimate the maximum or minimum size of the graph or set satisfying the certain requirement. Today, I just talk about the set. However, there are a lot of interesting extremal combinatorics problem on graphs. So, in addition, there are many certain requirements one says. However, today I just talk about the union free, P2 free, intersecting, T-intersecting, cross T-intersecting. Actually, there are a lot of the certain requirements on the set. For three distinct sets, if one is the union of the remaining two other sets, it is the union property. If it doesn't have the union property, it is called union-free family. In addition, for four distinct sets, one is the union of two other sets, and another one is the intersection of two other sets. It satisfies the P2 property. If it doesn't have the P2 property, we said it said family is P2 free family. In 1972, the Edwards are interesting there. The largest number of the P2 free subfamily of the M-sets family. So they got the upper bound of this number, and they conjectured the no bound of this number like that. This conjecture, this 40 years the Shadow conjecture solved by me and other co-authors. We solved this conjecture by using the probability method, exact deletion method. It's joined with Janusz Bartlett, Zoltan Freddy, Ida Kanter, and Balazs Packard. Actually, in today's talk, this conjecture is not main part, so I just give the simple example deletion method for the people who don't know the deletion method. So I define the independence number as the maximum number of the independent sets. Then, in 1987, Spencer got the no bound of the independence number like that when the number of edges is given. To prove this theorem, they just consider about the random subset. It means that we select every vertex independently with a probability P. Then we define the random variable x and y as denoting the number of vertices and the number of edges. In this time, there are both ends or must in the set S. Then, whenever there exists edge in this random set, we just try to delete the one vertex from this edge. Then, what happens here? You can get the independent set. Whenever you find the edge, in this random set, let's try to delete the one vertex from each edge. Then we get the independent set x prime of the size n is x minus y. So you get the new bound of this independent number like that. So it's a simple example deletion method. We solved this adversarial conjecture by using this simple deletion method. So let's move to our main part in today's talk. In today's talk, you are interested in the intersecting property. What is intersecting property? If there is intersection between two sets, but if there is intersection between two sets, it is called intersecting family. So the simple question is what is the maximum size of the intersecting family? If we choose the all subset containing the one fixed element, there should be intersecting family because it's contained one fixed point. In addition, the size of this family should be 2 to the n minus 1. So it's a simplification. And next step is what is the maximum size of the K uniform intersecting family? K uniform family means the size of the all sets has the same size. So the size of the all sets in this family is K. We said this family is K uniform family. Then what is the maximum size of the K uniform intersecting family? If n is less than 2K, you can choose the subfamily or K element subset. Then every pair of the all K element subset must have the non-empty intersection. So this case, the maximum size of this subfamily is n to K. How about second case? If n is greater than or equal to 2K, we take the all K element subset containing the one fixed element. That should be intersecting with the size n minus 1 choose K minus 1. So the theorem is about getting the maximum size of the K uniform intersecting family is very famous and well-known theorem. This theorem is called Adams-Collat theorem. Actually, the Adams-Collat theorem is a very central result in the combinatorics area. It's published more than 100 papers related to this theorem. In addition, it is solved by the many methods, such as shifting and shadow, the secret permutation, and algebraic method. Now, let's look at another property, t-intersecting property. What is the t-intersecting property? If the size of the intersection of the two sets is greater than or equal to t, this subfamily is called a t-intersecting family. If t is 1, it's just intersecting family. And what is the maximum size of the K uniform t-intersecting family? Yeah. The maximum size of the K uniform t-intersect family is n minus t choose K minus t. The Adams and co-Adams-Collat also got the maximum number of their K-uniform T-intersecting family like that. In addition, by Frankel and Wilson, they found the exact minimum number N0, satisfying the generalized Adams-Collat theorem. So, there the exact number N0 is there. They found the exact number N0 is the T minus 1 times K minus T plus 1. Instead of the T-intersecting and K-uniform, we just consider about the L-intersecting. Set L-intersecting and set K subset. What is the set L-intersecting? The side of the intersection of the two sets is in the set L from L1 to Ls. It is called set L-intersecting, and in addition, there are side of their set is in the set K from K1 to Kr. It is the set K subset of subset. In 1975, Lechather and Wilson got the upper bound of the K-uniform set L-intersecting. In addition, in 1978, Deja Aros Frankel improved their previous upper bound, so they got the upper bound of their K-uniform set L-intersecting like that. In 1981, Frankel and Wilson got their modular version of the Lechather and Wilson result. They got the same upper bound. This family is there. Set L intersecting one modular P, and also it's a K uniform on modular P. Here, this K is not in the set L. Then they also got in this condition, they got the same upper bound with the Lechather and Wilson result.
Was it about K uniform case, or maybe the sets have the size modular K modular P, or?
No. It's just K uniform. Yeah. In 1991, Noga Alon, Babai, and Suzuki got their upper bound of this set family, satisfying this condition. First one is the set L intersecting on modular P. In addition, the side of this set should be in the set K from K1 to K1 modular P. If it satisfies these two conditions, R times X minus R plus 1 is less than or equal to P minus 1, and N is greater than or equal to S plus maximum of Ki. Then they got this kind of upper bound. Then, in the same paper, Noga Alon and Babai Suzuki conjecture this kind of thing. They are in the same condition. If it satisfies only one condition, you have to drop by their one condition here. So, if under the only one condition, N is greater than or equal to S plus maximum of Ki, then the same upper bound holds. So they conjectured this one. Then this conjecture considered by many others. First one, in 1994, Snebeli proved that it's true well for N is for sufficient large N. In addition, in 2000, the Lechather and Chiang prove that it's true if n is greater than or equal to 2s minus r. In 2010, Huang and other co-authors considered the non-modular version of this conjecture. And legendary, we prove this conjecture is true and true. So it's a joint with Kyung and Huang. So it published in the European Journal Combinatorics soon. And we proved this conjecture by using the algebraic method. So let's look at a very simple example of the algebraic method. In 1983, the Deja, Frank, and Singhai got this kind of result. They said is L intersecting on modular P, and their size is not in the set L, one modular P. Then they got this kind of upper bound. So to get this kind of upper bound, we define the characteristic vector of each set Fi in this family F. Then we define the following polynomial for the S, the nth variable consisting of their 0 or 1. So satisfying their Si square is equal to Xi. Because of that, this this polynomial should be multilinear. From these two conditions, we get the f of vi is not equal to 0, 1 modular p, and fi vj is 0, 1 modular p for I is not equal to j. Then the set of this polynomial should be linearly independent. Then the all polynomial it have a degree less than equal to s, so we get this kind of upper bound. So upper bound is the sum of their n choose I. It's a simple example of their algebra methods. By using this kind of algebra method, we prove the Alon-Baba-Isuzuki conjecture. And in the non-uniform version of the Adams-Coral theorem, the maximum size of the intersecting family is like that. If n is greater than or equal to 2k. In 2014, Alon and Adrian and Huang got the same upper bound with a weaker condition than the intersecting family in the non-uniform version. So this one is the weaker condition than intersecting property. So this means they give a strengthening of their Adams-Coral theorem for the intersecting family case. Here, so we give their strength of their generalized Adams-Coral theorem. So we extended their result to T intersecting family. So we give their strength of their generalized Adams-Coral theorem by putting the weaker condition, then T intersecting property. What is T intersecting property? I already mentioned T intersecting property. Yeah, I already mentioned it. Yeah, so actually if you look at in the non-uniform version of the generalized Adams-Coral theorem, we get this kind of upper bound of their T T-intersecting family like that. So if you get at Noga Alon, Adrian, Huang result, it is just T-intersecting family case. So it is just T1 case. However, we extended this result to the T-intersecting family. So all T is a joiner with Dong Kang and Younjin Kim. So
Right?
yeah.
Yep.
어떻게 하지? 들어갔지.
Control.
일단 뭐지?
계속 하셔요.
이거 크게 하려면
Control. Control.
컨트롤 N이야?
스킵 한번 눌렀다가.
아닌데.
다시 한번.
So our result is extended the Noga Alon and Adrian Huang result to all T. So it's a joiner with Dong Kang and Younjin Kim. So in addition, we also give the strength of the box result related to the cross T-intersecting case. What is cross T-intersecting? The side of the intersection of the two sets is greater than equal to T. Here, these two sets are selected in the different set family. Then we say that this set family is cross T-intersecting. So we give the following strengths of the both result related to the cross T-intersecting case. In addition, the following Roloff's two families theorem was very famous and well-known result in the extremal set theory. And for the finite connection of the set here, satisfying these two properties, the intersection of AI and BI is equal to empty set, and intersection of AI and BJ is not empty set. Then satisfying this equation is Roloff's two family theorem. And in 2004, Tabo extended their previous Roloff's two family theorem to two T-intersecting family. So they got this kind of result for the T-intersecting case. So they proved this theorem by using the induction. Here, by using the probability method, we proved the previous table result and we give the slight improvement of the table result. So actually, after putting the weaker condition than the previous one, we get the same upper bound. Actually, T should be greater than equal to 1 here.
So what's the difference?
It's the third condition should be different. It's slightly different. Yeah. So, yeah, this is joiner work with Dong Kang and Younjin Kim. So, I'm interested in the following open questions. So, as you know, for the Adler's cross theorem, there are a lot of methods to prove that theorem. Compared to this theorem, there are no other proof of the generalized Adler's cross theorem except for the Franklin Wills proof. So, I'm very interested in getting a new proof of this generalized Adler's cross theorem by using the shifting method. So actually, there is. In addition, in 1988, many chemical classes in Singai conjectured the following theorem. If you consider every set of the n real numbers with a non-negative sum, this one has n is n minus 1, choose k minus 1 k element subset with a non-negative sum. This conjecture was, is considered by the many others. Actually, there are more others. However, I just put just three measured related to this conjecture. So in 2012, Alon, Huang, and Stakov gave their first polynomial bound for this conjecture, and allegedly, Chaudhry and Sakis and their Sarieri proved this conjecture. This is true if n is greater than or equal to a k square, and Pocklow's scale is true if n is greater than 10 to the 46k. So I would like to verify this conjecture. So thank you.